In this video, we're going to cover the fundamentals of transformations. This will include using the point form notation to apply dilations, reflections, and translations. Enjoy. Okay, so today's class we're going to have a look at transformation fundamentals. So we'll cover all the fundamental kinds of transformations that can be applied to all sorts of different functions. And we'll also look at what happens if you apply a sequence of transformations, so multiple transformations on the same function, effectively. Now, you would have already seen a whole bunch of examples of this: polynomials, quadratics, and all of the functions we did in the miscellaneous functions. Everything has transformations in it, and they can compound onto each other to create all sorts of different functions. What we're going to look at is a way of generalizing that across all possible functions. And the kinds of questions that get asked around this, I find is easiest to work with this process that we'll go through today, which is sort of working on transformations in terms of how they're mapping the original x, y coordinates from one equation to some new mapping somewhere else. Because that's all effectively what transformations are doing. You have some initial x and y coordinates and you're moving them somewhere else. That's what this is going to be all about. Now, this is going to seem overkill when we're talking about individual transformations. It'll become more helpful when you're dealing with a sequence of transformations, and then again more helpful when you're dealing with going the other way around, which is, here's a transform function, how do I get it from one state to another? So it'll be more helpful later on. Okay, first up, dilations. So dilations are all about stretching your function. You either stretch along an axis or from an axis. Both of those wordings are correct. The from an axis is a lot more common. That's what's used in the Cambridge book, and I think also in the Jacaranda book. Although I have seen along an axis be used before. So essentially all that's happening there is it's more of an English thing, really. They both mean the same direction. If I were to draw an axis, I could say I am moving along the y-axis, in which case I'm moving in the y direction. But another thing I can say is that this is also going away from the x. So, all that to say, both of those mean the same thing. Now, as for how we actually represent that in a function, well, dilations are pretty much always going to be a multiplication on a particular variable. When you're going in the y direction, the multiplication is going to be on the y variable. So you're starting at some initial coordinate x and y, and you're getting to some new coordinate x comma a times y, where a is your dilation factor, whatever that happens to be. So, as far as the steps go, first things first, you want to identify what your transformation is. The new x dash, is going to be the old x, because it's just a transformation on the y so far. And the y dash, the new y, is going to be a times y. From there, you want to rearrange to get in terms of the original x and y. And the reason why is because you're going to try and sub it into the function, whatever that function happens to be, and your function is in terms of x and y, not x dash y dash. So just a quick rearranging there, nothing too crazy. And then, yeah, as I said, sub that into the function, whatever that function is. So instead of having y equals f of x, you now have y over a equals f of x. So you replace every y with this, you replace every x with that. Now when you sub it into the function, we drop off the dashes on all that notation, because mainly this is just for us to figure out like where are we starting and where are we going. When you give the final function, you drop all that notation off. Now, we've replaced our y with y over a. That's not really great for functions, though. When we write our functions, we want to have y entirely on its own, so all we end up doing is multiplying both sides by a to get the a on its own. So, in summary, if you want to apply a dilation along the y or from the x, it is a multiplication across the entire function, whatever that function happens to be. For those who have joined us relatively recently, we're going through a process that will be more effective for the later stuff. This does seem like a bit of overkill for what we're talking about now, but this will come in handy a bit later. if your a value is greater than 1, so starting to deal with +2, +3, that sort of thing, you're stretching further along the y. If it's between 0 and 1, you actually shrink. So instead of going further along the y, you go closer towards the x, essentially. So here's an example with a basic function, square root x. If you want to apply a dilation factor of 2 from the x, so remember, from the x means in the y direction, the y value is going to get multiplied by 2. If you're just using the shortcut, by all means, this is a pretty simple example. Just multiply your function by 2. If you've got a more complicated question, you might want to follow this process, which is x dash y dash, rearrange, and then sub in. If anyone wants me to dive into that in more detail, let me know. Otherwise, we'll continue to move on. Similar thing here. Dilation in this time, it's in the x direction. So either along the x or from the y. As you might expect, now we're just multiplying the x instead of the y. Exact same process, but now when you sub it into your function, you'll notice that there's no further rearranging to be done here. It stays and still appears as a division. This is where things start getting a bit weirder, because this a here is still your dilation factor. So in one instance, it looks like a multiplication. In another instance, it looks like a division. But if this was like if we had the example here, this divide by 2, this is not a dilation factor of a half anymore. This is a dilation factor of 2. It just appears in a different spot. So I guess that's another reason why going through this procedure is a little bit more effective, because it means you don't have to worry so much about the way the function looks, because you can always just go through here and know from the very beginning, yep, dilation factor is exactly what I say it is. Fair enough on that. Let me know if not. Reflections. So you guys have seen this before. Reflecting in an axis, either in the y or in the x. Whatever axis is mentioned, it means the opposite sign, the opposite value gets the negative. So if it's the y-axis, then the x gets the negative. If it's the x-axis, then the y gets the negative. And the reason why is because if you're reflecting in an axis, that axis acts like a mirror, essentially. So if I were to draw another axis, and we have our y, reflecting in the y means this is our mirror, this y-axis. So if I have a point over here, the reflection of that would bring it over here. And what we might notice is that the y values, this is horizontally the same, so the y values are the same, but if you look at their equivalent x coordinates, they flipped. So the x is going to hit the negative. Otherwise, the rest is the same. So you do your rearranging, and then after subbing it into the function, you'll notice it's still the x that gets the negative on it. Here's an example where you've got multiple x's. You treat it the same way. So if you go through the process, then by all means. Otherwise, just replace each of these x's with a negative x, and then simplify from there. Reflection in the x, again, going to have a negative on the y this time. Normally when you sub it in, it'll end up on the left because it is a y transformation, but we manually move it over. So reflections in the x can always be done by making a negative on the entire function. Do I have a good... Yeah, I do. So when you do reflection in the x, it's not like you just want to put a negative on this, just out the front. You want to put a negative on the entire thing. And one way that I like to do that more recently is to put my negative literally on the y, so I don't forget that it has to go on for the entire function. So when you get that y back on its own, both of these become negative. And then translations. So this will actually explain why x minus a is a shift right. The reason why is because of this like inversion that you have, where when you want to go horizontally, initially you do in fact do an x plus a. So you shift right by whatever a is. But when you go through this whole rearranging and subbing it in, because you've rearranged for x instead of x dash, that plus a now looks like a minus a. And so when you put it into your function, an initial shift right, x plus a, now looks like a minus sign. The reason why that doesn't happen for the vertical translation is because when you flip it to a negative, it appears on the left. And so we once again chuck it over to the right. So it flipped twice. Positive, negative, and then back to positive at the end. So that's a bit of behind the scenes as to why the x minus a is shifting right. But otherwise, yeah, we're just following the exact same processes. Okay, so we've gone through all the fundamentals there. Now, this is where our procedure becomes a little bit more handy when we deal with sequence of transformations. This is where you have multiple transformations you need to do in order to whatever function you have. I've got the procedure written out here. We'll go through it in an example just so it's easier. The key thing I want you to be aware of is that the order in which you do things matters quite a bit. So what I've got here are two examples that have the exact same transformation factors in them, but they're just written in a slightly different order. So in the first example, we had a dilation of factor 3 from the x. Reminder, from the x means it affects the y, so it multiplies the y. Next up was a reflection in the x. So once again, the y value, the y variable, is going to get the negative. Now, when you think with a sequence of transformations, you pretty much just leave up. You start the next one where you left off. So we left off with x and 3y, and so when we put our negative on there, it's going to go on this entire spot here, the 3y spot. And then lastly, we had translation 5 in the positive x, 1 in the positive y. So where we left off was here. The x is going to get x plus 5, and the negative 3y is going to get a 1 added to it because of the 1 in the positive y. And then that's our final transformation right there. This is your x dash, this is your y dash. If you want to apply that to a function, then, well, then you've achieved exactly what you want. I'll spare the major details as to the differences here, but basically, in this second example, we applied the transformation for the translation first, then reflection, then dilation. And what you see is the end result is, sure, the x dash is very similar, but what we find is that the y dash is also kind of similar, but there's a pretty significant difference when you compare the two. Expanding this out will give you negative 3y minus 3, whereas this one's a plus 1. So, all that to say, order matters. Okay, that's it for the theory there. So as far as we can access this, I've got all the summaries here of all the key things you need to do, as well as all of the shortcuts. If it's just a simpler example, you would just go straight to that. So what I'll do is grab a screenshot of all of this. We'll put that in the chat, and unless anyone wants me to clarify anything, we can start getting into some questions. Maybe I should grab this one differently, actually. I should fix this page break. Cool. Okay. So that's pretty much it. Let's get into some. So yeah, I'll do one of these quote together, and then I'll field some questions. Okay. The first question of 7a is a little bit weird-ish because I didn't really explain exactly how you handle it when it's just a point, but I wonder if anyone can tell me how you might handle it. We have a point, negative 3, 4, and we want to know where that point ends up after we shift 2 units in the x direction and 3 units in the negative y direction. What might we do?
Just go step by step, adding the numbers according to the coordinates.
Yep. What would that be then?
So after this, um, the x point would become -1,
Yep. So we got
and
negative 3 plus 2. That's good.
the y point would become 1. So the final coordinate would be -1, 1.
That's it. Yeah, precisely. So you just go in order. The first one was 2 in the positive x, so you would have added 2 to this. And then this one was a minus 3 on the y. And so sure enough, we get to -1, 1. That's exactly right. D is a little bit different, but it's only like this is the worded version in part A. D is just the mathematical version of that. Can anyone tell me what D is going to end up making the final point look like?
-7, comma 9.
Yeah, there you go. So basically, for everyone else, whatever your x value is initially, in this case it was -3, you do a subtraction of 4. Whatever your y value was initially, you add 5 to it. That's all that's saying. Okay, that's that. This is going to be simple. And now we get into some actually applying these transformations. So let's see. Yeah, they're all basically the same thing. So we'll do A in this case. Let's see. F of x was 1 over x, and we want to do 2 in the positive x, 1 in the negative y. So either tell me what the final function would be or how you would figure it out.
1 over x minus 2, and then -1 outside of the fraction.
Yep, that's it. 1 over x minus 2. And then, would you say for the last one, sorry?
-1 outside the fraction.
Yeah, -1. That's it. Yeah, precisely. So these are on the simpler side. You don't have to worry so much about order because there's no, it's all just translations in this chapter. So you can just go straight into the function. It was a shift 2 to the right, so it's always x minus your value for horizontal. And then, well, it was a shift down, so you got the -1 out the front. That's pretty much it for that chapter. We'll do like a dilation and a reflection, just so we know we're doing the right values. Let's see. Nah, the point one's a bit... Yeah, actually, no, point one's probably a decent example for it then. So, we got the point, -2, -3. What's it going to look like if we reflect in the x?
-2 and +3.
Yep, -2, +3. Reminder for everyone else, if the x-axis is what's mentioned, then it's the other value, the y, that gets the negative on it. And then dilate factor 4 from the y. What's that?
Is that -8, comma -3?
Yeah, that's it. So from an axis means it goes on the opposite variable. This will be consistent across the entire book. So if you know this one, you'll know the entire book. I just put it in there anyway, just in case it does say along in an exam, because I have seen it, not necessarily in a VCAR exam, but in a past exam, maybe from TSSN. I don't quite remember exactly where I saw it, but it was probably worth putting it in there. And then, yeah, that's what all that starts looking like. So everything 7a, 7b, you can just like directly sub in, even with these functions here. 7c starts getting a bit more important because, well, as we saw, dilations and reflections will behave differently if there's already a translation term in there. So going direct to function, it's doable, but risky depending on how well you do it. The point isn't going to be anything crazy. Let's see. Yeah, we'll do question 2 on this one. Okay, so we have y equals square root x and 2a. We got a translation followed by a dilation. So how do we start this one off?
Would that be root x minus 2? Sorry, or let's see, like root x minus 2, would it be all over 3?
Root x minus 2 all over 3. Not quite. Did you go and sub directly into the function, or did you follow the x dash y dash stuff?
No, I just went straight for the substitution.
Yeah. So what you've been caught out is the same thing that everyone gets caught out with, and that's the fact that subbing directly in, like, here's a dilation from the x, it looks like a multiply. Here's a dilation from the y, it looks like a divide. Translation in the positive direction looks like a negative for the horizontal, looks like a positive for the vertical. There's a whole bunch of different rules for different things, and if you're not super confident with them, then you can definitely get caught out on that. Basically, instead of dividing by the factor, you should have multiplied, but otherwise everything else is fine. Now, what I was going to say, where it gets even more trickier is when the translation and dilation are on the same axis. So if this was a shift 2 up and then dilation 3 from the x, then under those circumstances, this translation also gets multiplied. So not only do you have to worry about this, but also the order of operations when you do them. Bit trickier. But okay. So to follow the actual procedure, what I would recommend you guys do would be start by identifying your x dash y dash. So you start with some xy. The first thing that was mentioned was translation to in the positive x. So that means we go to x plus 2 and then y. And then lastly was a dilate factor 3 from the x. So x plus 2 and then 3y. From there, that means x dash is x plus 2, y dash is 3y. Next step from there was rearrange in terms of x and y, because we're not going to try and chuck this into a function. So that means getting the 2 to the other side, x equals x dash minus 2, y equals y dash on 3. Now from there, our function was y equals root x. Every y is going to be replaced with y over 3, that's what this says, and then every x is going to be replaced with x minus 2. And then from there, to finish it off, y equals 3 root x minus 2. No hassles, no worries. So yeah, there's, more working out. One way you could do it, if you're doing it by, do I have it in this note? No, it's in the next note where you're doing it. The other approach is just doing it like by recognition, which means you start with your root x, and then from there, when you apply the translation next, you then say, okay, I got square root x minus 2. And then the next thing would be, okay, I got my dilation factor. Now, the thing that confuses, is this it? Like even I'll, because I'm so used to this procedure, I might get this next one wrong, but I'm pretty sure if you then go ahead and try and do a dilation on this x, it means replacing every x with that dilation. So when you do your 3 root, like let's say we're doing a dilation factor of 2 from the y, I believe that now looks like this because you're replacing every x with x divided by 2, and that's what that looks like. But I think a lot of people, and will just go and divide the entire thing by 2. Yeah, it's one or the other of this, and that's the weird thing to me. Point being, do the x dash y dash, and you'll be pretty happy that you've done it.
Chris,
Yeah.
can you show us a practice question for this example, like a similar one that would like have a dilation on the x?
Dilation on the x after a okay.
Yeah, so like from the y.
Yeah, okay. Let's see if we can find one that's pointing in the same direction twice. Translation. That's dilation then translation, so not super crazy. Oh, maybe this one actually. Yeah, let's see if this one does it. Okay, so we still have y equals root x. So we start with xy, maps to dilate factor 2 from x, so from x means along y, and then translation 2 in the positive x means we get x plus 2 comma 2y, and then 3 units in negative y, x plus 2 comma 2y minus 3. That gives us our final point, so x dash is going to be x plus 2, y dash is going to be 2y minus 3. Next stage is to rearrange for x and y. X equals x dash minus 2. Let's do this in stages so we can all follow along properly. Y dash plus 3 equals 2y. And then finally, y equals y dash plus 3 all on 2. Yeah, okay. So there's the... Yeah, there's the gimmick. So when you have dilation first, then translation, it looks like the whole thing's been divided. Whereas if you do translation first, then dilation, it's the opposite. Only the variable gets divided or multiplied, whatever that looks like. So I was right initially when I was talking about this one here, which isn't very intuitive in my opinion. So that's my case for doing this instead. But okay, let's finish it up. Y plus 3 over 2 is equal to square root x minus 2. So every y got replaced at this, every x got replaced at that. Y plus 3 equals 2 root x minus 2. And then y equals 2 root x minus 2 minus 3. So that's all. If you follow the x dash y dash thing, you're doing the exact same thing every time. You're relying on your algebra skills. Whereas if you're doing by recognition, I guess it's also your algebra skills, but I guess you're more so now dealing with composite functions, where this one's like, I want to go from f of x to f of x minus 2. And then this one is going to 3 f of x minus 2. And then, yeah, even with this notation, it still looks weird. It's almost like you got to do each individual function on its own. So f of x minus 2 we could call g, and then the next thing would be 3g of x, I don't know, call that h, and then h is now, yeah, h of x over 2 is your new function, whatever. At each stage, you're only replacing the x with the new thing, or the y with the new thing, and that can get confusing. Feel free to do it though, if you prefer it. But okay, that's that one there. Anyone want me to clarify any of those approaches? Otherwise, we'll move on to another one, which to me would be part 7. Now you've got an already transformed function, and you want to see what happens when we apply further transformations to it. Y equals 2 bracket x minus 2 all squared plus 3. And our transformation list is shifting 2 in the negative x, 3 in the negative y. Nah, I don't like that one. Where's a better one? Reflection, translation, or reflection dilation? Yeah, let's do B. So reflection in the x followed by translation 3 in the y. How do we start this one off?
Would you want to establish like what your x and y's are already like looking like?
Yeah, precisely. So you have your xy initially, and then we got to figure out now what's being done to them. Absolutely. So the first is a reflection in the x. What does that look like?
We multiply the y by
That's it.
-1.
Very good. And then finally, you had a translation of 3 in the positive y, which would mean what would the final point? Oh, sorry, P. I just saw the answer there. My notification was covering it up. Yeah, you've got it, P. That's good. You also then add the +3 because of the translation of 3. X comma negative y plus 3. Perfect. So that means that our x dash is just x, so nothing crazy there. And our y dash is negative y plus 3. What do we do with that?
Chris,
Yo,
Never mind.
what's up?
how would you, just a question, how do you know if there's a reflection in the air? How do you know if it's a negative y?
Because the axis that's mentioned is always the opposite of what variable you put it on. As far as y that is, if we go back up here, this is my little diagram of what a reflection in the y would look like. We did this one earlier, which was whatever axis gets mentioned acts like a mirror, effectively. And so if this is our initial point and the y is a mirror, then the mirror reflection of that would mean the point gets shifted over here. From there, if you compare the new x and y values between them, horizontally, these are the same thing, so y values are identical, but vertically, this is a different x to this. And so the x's being different mean the x value is what gets the negative on there.
Okay, over.
Cool. Opposite for this one though, because this was a reflection in the x, so the y gets the negative this time. Okay, so x dash y dash, what are we doing with them?
We replace all the y's in the pre-existing function negative y plus 3, and we can just leave x alone because it hasn't changed.
Pretty close. There is one minor step that we've missed, which is we have a function y equals 2 x minus 2 all squared plus 3. I can't actually sub any of this in yet. I mean, this one I can, but I can't actually put y dash into this spot because y dash and y are different. So the step that's been missed there is you rearrange this first, then plug it in. Clear enough? So rearranging it, if I just knock this out the way, you'd have y dash minus 3 equals negative y, and then y equals 3 minus y dash. From there, now we do what you suggested, which was replace every y with this, and then just leave the x on its own because, well, there's nothing done there. Why won't this camera focus? There we go. So 3 minus y is equal to 2 bracket x minus 2 over all squared, and it was plus 3. I did get all those. Yeah, I did get all those right. And then from here, well, nothing crazy at this point. Just do your algebra. So 3 is going to cancel, nice and easy. And then y becomes negative 2 bracket x minus 2 all squared. That's using the point form variant. I'm going to try to do it by recognition. Let's see. So we start with y equals 2 bracket x minus 2 all squared plus 3. We're told the first thing is a reflection in the x, and so the y gets the negative, which would mean we now have negative y equals all that, or y equals negative 2 bracket x minus 2 all squared minus 3. And then 3 units in the positive y means this negative 3 gets added 3 to it. And so y equals negative 2 bracket x minus 2 all squared minus 3 plus 3 gives you 0. So whichever one of those makes more sense to you or feels better for you, feel free to use either. My personal preference is the first. Okay, that's that one. Let's see. Is it worth touching the CAS one for now, or maybe we'll even do. What do you think? CAS next, or we try this hyperbola, which will more or less be the same idea. We did any more practice with these, or shall we move on to a more complicated CAS question?
Can we do the CAS one?
Yeah, sure can. Just a second while I take a sip. Okay, it says CAS. It doesn't look like you need it based on what I'm seeing here, but I guess we'll see. So, we got a quadratic. It's shifted a in the positive x and then dilated k from the x. And then we're told 2 points that new graph passes through. By the way, if it wasn't super clear, the image of a graph is just what it looks like after transformations have been applied to it. So it basically means after transformations, it passes through these points. Figure out what a and k are. What should we do? I'll let you take a moment to think if you need.
Would you set them up as simultaneous equations?
Yep, simultaneous will be required, absolutely. It's a bit early to set up the simultaneous right now because we don't actually have any equations to put them into. How can we get those equations?
Would you want to apply all the transformations first to get the new like x and y's?
That's it? Yeah. What's that going to look like?
So first we go x minus a comma y.
Yeah, x. Oh, let's try it in green this time.
The positive translation of a units.
Well, x minus a. If we're doing a point by point thing, because it's in the positive direction, you start with a plus. If you're shifting by a in the positive direction of the x. Granted, they didn't necessarily specify that a could be positive or negative, so that's more of a book thing. I think you're supposed to assume that a is going to be positive. So, like, shifting a units would in fact be a plus. That's the only weird thing about doing the point form, I find, which is it's already been beaten into you that horizontal translations look like that when they're in a function, but when they're in point, they are what they are intuitively. But yeah, so the first one will be x plus a comma y, and then followed by a dilation factor k from the x would be what?
Would it just be ky?
Ky. There you go. X plus a comma ky, which means x dash is therefore x plus a, and y dash is therefore ky. Okay, what else now? Rearrange, yep, that's it. So rearranging for x and y, it's going to give us x equals x dash minus a, which is now it looks like the minus a we were expecting. And then we got y equals y dash over k. Rearranging has been done. Where do we go from there?
We substitute.
Yeah, sub into function. So original function was y equals x squared. Every y gets this, every x gets that. Y over k equals bracket x minus a all squared. Y equals k bracket x minus a all squared. That's that one. So there's the point form. For those who prefer recognition, y equals x squared. Translate a in the positive x would mean replacing every x with x minus a. And then dilate factor k from the x looks like a multiplication of the entire function. And so k bracket x minus a squared. Cool. All right, that's that. Now, I heard it earlier. We now have our equation to work with. What are we doing with it?
We sub in the points.
Sub in the points.
Yeah. So we can create two new equations.
That's it. Yeah. So this shouldn't even be too hard to do by hand, but I guess we'll see. So the first one's going to be 1, 1, which means y equals 1, x equals 1. AR squared. That's equation 1. And then equation 2 was just x equals 2, y equals 4. 4 equals k bracket 2 minus a all squared. Now, if you had to do this by hand, what might you do?
Would you multiply the first function by 4?
Potentially. So if we do that, that'll become 4 and 4k there. Where might we go from here if you do that?
And then we can just like equate the two equations to each other.
Yep.
Like 4k times 1 minus a squared is equal to k times 2 minus a squared.
Yep, we can make those equal to each other. Now, we still have the issue, which is there's still now multiple variables in the same equation. How do you handle that then? And I'm actually asking because I don't think it's doable that way, but it could be. I just haven't done it before. I don't, because like you got these initial equations 1 and 2. Because this third equation was created by 1 and 2, you can't like sub in another 1 or sub in 2 into this new equation where you've equated the two together, because then you just get 0 equals 0 in most cases. Yeah, don't think it can be done, but good idea, right? You're trying to look for a substitution method, and substitution does work. It just means that when you do your substitution, you want to make sure that you're replacing a variable, not a number. So if we get it back to where we started, if you want to do substitution, one thing you could do is divide both sides either by that or by that. That would get k on its own, and then you can replace k with something purely in terms of a, solve the a, plug it back in for k. That's one way of doing that. So just to do proof of concept there, if I rearrange equation 1, it would be 1 over 1 minus a all squared equals k. So dividing by that, and then replacing every k with this in equation 2. 4 equals k, which is now, well, we can just do our this, and then because it's a fraction, put this over on the bottom. And now we've got it in a situation where there's only one variable. So that's one way of doing it. You just expand this, well actually no, you don't expand, sorry, you would square root. That's much stronger. Square root both sides of this equation, and the reason why that's good is because both of these terms are squared. So when you square root an entire thing, it's the same as if you distribute the square root between the top and bottom. So square root both, 2 equals 2 minus a on 1 minus a. Rearranging that is now not so bad. The other approach, well, I guess first, clear enough how that works. Hop off mute if you need to clarify. The other way is elimination. So what we can see is if we were to, oh, I heard a noise. Is that a question or?
No, sorry, I just dropped my pen whilst I was on.
You're good, man. You're good. Okay, the other would be elimination. So what we can see is, well, if I did it in the right color, if you were to divide both equations by each other, then the k would cancel. So you can do it either way, 2 divided by 1 or 1 divided by 2. It's the same stuff no matter what. Let's see. Yeah, I'll just do it down here instead. So it would be 1 divided by 4, so those two divided by each other. K divided by k, which, well, they cancel, that was the whole point. And then 1 minus a squared divided by 2 minus a squared. And when I write this out, you'll notice a pretty significant similarity to what we had before, which was this is just that flipped on its head. So, same thing. Still go ahead and do your square root of both sides. The fraction here just looks a bit weirder. So literally, if I had just done 2 divided by 1 instead of 1 divided by 2, I would have just got this off the bat. So elimination is slightly faster in the sense that you get there one line earlier. You just don't write this, but it's whatever. All right, so we'll finish that solution just so we can do the rest of the question. 2 bracket 1 minus a equals 2 minus a. 2 minus 2a minus 2 plus a equals 0. Minus a, so just a equals 0. Yeah, a equals 0 there. 2 equals 2, yep, checks out. So we got our a equals 0. Someone take it home. How do you finish it?
I still got it.
Are you subbing the a into one of the equations?
78 are one of the equations, yeah. Sweet, cool. So they're basically the same thing. So sub in a equals 0 there, you're going to get k equals 1, right? Because 1 minus 0 is 1, 1 squared is 1, 1 times k is k equals 1. So, final set of answers, you would write a equals 0, comma, k equals 1, and then you're happy. So, to reiterate, first step was applying our transformations, whichever method you prefer to use. Apply the transformations, you get your equation. From there, it becomes a simultaneous, like you guys are probably already used to a lot of. A lot of the previous chapter on miscellaneous functions does a lot of that. So you do your simultaneous, whichever way you like, substitution or elimination, both are fine. And that gives you your answers. Now, as for the CAS portion of it, just so you guys are aware, simultaneous on the CAS. So for TI Inspire, menu 3, 7, 1. So this sole system of equations here. You click that, number of equations, however many equations you're doing, and then variables. You can keep them x and y, but I would prefer to write the actual variables so I don't write the wrong thing on the page. Apparently my a is already defined as something, so this isn't going to work super well. But yeah, you would just then plug in your equations, whatever they were, into this spot. A pro tip for it, well, first I'll even explain that. So I'll just put the a back in there. If you ever see a bold letter, it just means that you've already assigned that variable as something. And so basically, unless you've deliberately done that for a reason, if you see a bold letter, just kill it. And you can do that through menu 1 and then delete variable, so 3. And of course I misclicked it. Delete variable, and then whatever that variable is will no longer appear as bold. Now, the pro tip that I was going to mention. If you have a generic equation to work with, my recommendation is define it to start with. So we had this. We're just going to define this function, so we don't have to type it in a bunch of times. So h of x is now going to be k times bracket x minus a all squared. You'll notice that h is bold because we've just defined it as something, and a is no longer bold because I deleted the variable, whatever it was, probably a slider. Okay, now that this is defined, when we go through and do our simultaneous with our a and k, all we've got to do is plug in the points. So the first one was x equals 1, y equals 1. And the second one was x equals 2, y equals 4. And that's actually given us a set of 2 solutions. Uh-oh. What did I do a little bit wrong? Oh, it was a plus minus, wasn't it? Damn it. Oh, it's totally the plus minus, isn't it? Whoops. Yeah, if you plus minus this, you would also have negative 2. Those cancel. 1 minus a. Negative 2 bracket 1 minus a. 2 minus. Oh, whoops, that's not how that works. 2 minus a. And then minus 2 plus 2a equals 2 minus a. Minus 2 plus 2a. Minus 2 plus a equals 0. Minus 2 make minus 4. And then plus 3a. Yeah, okay. So I just forgot to do my plus minus. That's why there's an a equals 4 over 3. And so if you were to sub that back into the original equation, you would get the k that came up on the cas. So good thing we did it on the cas, otherwise I would have forgotten that. There you go. Easy mistake to make, apparently. So anyway, that's the TI Inspire version. For those using Casio, it's a little bit weirder. So same things I'd recommend, which is define your function first. So this is where it gets a bit nastier, because now I've got to use the keyboard on this, and I'm significantly slower with this. X minus a. Oh, yeah, that checks out. Yeah, that's fine. I can complain about that. And then the simultaneous is in, I think it's the math 3, isn't it? My camera's in the way, so it makes it hard to see. It is... Was it math 1? Oh, it is 2, yeah. The simultaneous equation solver is that one. And if you need to do multiple lines, you would just keep hitting that for multiple equations. For us, we only need the one. So, no, that's not the right button. There it is. And now again, we can do our h of 1 equals 1, and so on. h1 equals 1, and then h of 2 equals 4. At the end, you just want to put the k in a. So, k, comma, a. That's just complaining about things from before. What? It's not even going to do it. Wow, simultaneous equation solver sucks on Casio. Unless I did something weird. Yeah. That's the equation we were doing. Damn. It's even weirder. Why would it not do that? Was it because I edited something? I'll just grab a copy of that and chuck it in. Alright, I don't like this Kaz. I don't know what's doing. Why does it not actually solve it? It's clearly got the right equations there. Did I plug the points wrong? It was h of 1, y equals 1, h of 2, y equals 4, yeah. And then equation was y equals k bracket x minus a all squared. Do we have that? K bracket x minus a all squared. Okay. Is h of x defined weirdly? Let's find out. Looks like it. Usually I should be able to print that. Why is it doing that? I might have to just like look at this in my own time. I don't know why the Casio decides to do weird stuff like this. Define h of x. Yeah, I'll suss this out. If I have a good answer for it, I'll make a post about it. But that's how it's supposed to work. Maybe it doesn't like the root portion of it. Actually, maybe that's why, because it's got a lot of commas in there. Anyway, that's about it really. For part B, it's the same thing. You've got two different points. Now it's just 1, 1, and 2, 2. You would presumably use the exact same methods to solve it. For those who use Casio, I apologize. But TI Inspire is the better Cas. Not just for this, but for a lot of things. Namely, like one of the things this Cas actually can't do is complete the square. So something as simple as that. This one doesn't do. TI Inspire does. I've yet to find. I found one scenario where TI Inspire wasn't a better calculator, and that was when it was doing a particular inverse around exponentials and logarithms. But otherwise, it's been superior. If I were to recommend, get TI Inspire. A little bit better. But okay, that's about it for pretty much all the questions here. If anyone wants to stay and have a chat for the last 2 minutes or so, feel free. Otherwise, the chapters are 7A through C on Cambridge. Do I have the Jacaranda? No. There'll be the Chapter 7 review and 14H as well, apparently. Why 14H? What's there? Oh yeah, circular function stuff. Okay, why not? Sweet. I'll leave you guys to it. Take care.